I think it's 11:40, so how is everybody doing today? I'm going to warn you, there will be some maths. In America, we only have math. Everywhere else, it's maths. Is it the same in Norway? Is it maths here? Or do you just say math? Singular? Okay. Because in the UK, they have more than us. We don't know what it is, but they have maths. All right, today we're going to do deep learning with TensorFlow. You're probably wondering why a Microsoft guy is going to talk about TensorFlow. And the reality is because we don't care what you run on our cloud. The slower, the better. That's for funny. Just kidding. That's not true. But when it comes to AI and machine learning in particular, there's been a lot of humanity's worst things that have ever happened, have come about because of AI. And what I want to do is I want to make sure that everyone knows that this is not this. And I feel like there's a lot of fear, uncertainty, and doubt when it comes to AI. And so today, because everyone wants to do the AI things, I'm actually going to show you how it works, all the way, especially with TensorFlow. Because my worry is that people are making AI and specifically machine learning and specifically deep learning into a marketing problem when in reality it's an engineering problem. So we're going to talk about it like engineers, and once you know what it does, then you'll be able to ask the right questions about your cloud providers. Does that make sense? I worry that we are talking about it from a marketing perspective way too much and not enough from a real life perspective. And so that's what the goal of this is today, is I want to talk about it from a real life perspective. So let's talk about AI as a huge bubble. That's probably not a good word to use in tech. Let's just say a big circle, AI. AI is anything that makes machines look intelligent. Machine learning is a set of algorithms that help you do that, and deep learning is inside of the other machine learning circle, okay? So if you think about it like that, that's the best way to think about it. Now, the way I like to talk about machine learning in particular is through a story. Does anyone work for a bank? There's always that guy. What's your name? Matt. There's always one guy that works at a bank. So let's pretend that one day Matt's boss, Susan, who's in charge of all the technical stuff, says, Matt, you're a good programmer, so we want you to do something. It's just this one thing. How many programmers have heard it's just this one thing and oh no, here it comes, just this one thing. Matt, what I want you to do is we have pictures of checks that we've scanned in, and we want you to write an algorithm to detect whether it's upside down or not. But Matt works for a cheap bank, and their checks have a black stripe at the top. Okay? Super easy. Matt is a really smart programmer, and so Matt says, sure, it'll take me 6 hours, which in programmer speak means 30 minutes because we take lots of breaks. All right, there's a YouTube thing, it came out, and then we have lots of tabs open that need to get read. There's a lot of stuff Matt needs to do, so it'll take him 30 minutes, but 6 hours, right? And so Matt is really smart, and if you're a programmer, how would you solve this problem knowing that there's black stripes at the top of your check? Well, our programmer lizard brains automatically go into a series of step things, right? We're trying to come up with the steps. That's what our programmer lizard brains want to do. And so he's like, what I'll do is I'll look at random 100 pixels at the top of the check. If they're all black, it's good. If they're not, I'll flip it, right? So 6 hours later, the boss, she comes down, and Matt's like, I did it. I'm a genius. It's actually, because we have a really good DevOps process, it's actually already in production. Matt gets a strong pat on the back, and he goes home. The next day, she comes back, and she's like, hey, that was such a good success. We just want to do this one more thing, just one more thing. It turns out the president of the company of the bank, he really likes his cat, Fifi. He wants, just for this one thing, he just wants his cat picture on just his check. That's it. But as programmers, we're like, well, crap. You know, if we do like this cat picture for his check, then we have to do it for all checks because someone might have the picture of the same cat on the check. And so our programmer lizard brains say, okay, what would you ask for if it's just this one picture? Well, can I have the picture, right? And then Matt, since he's very clever, says it'll take 2 days, really means 1 hour because we take a lot of breaks. And he finds a way to sample a random 100 pixels that he knows should be in this spot. And then he checks it, and then if it's wrong, he flips it. Good. So 2 days later, they come back, and they're like, well done. Our programmer's lizard brains are working. And then she comes back and says, because this was such a success, we want you to do this with any picture for any check ever. And now Matt, there's no amount of breaks that will help him with this, right? Notice that the problem went from something that we could, our lizard brain, programmer brains could come up with steps, to all of a sudden something that is not possible for our programmer lizard brains to come up with, right? There's like a huge jump between the cat picture, which admittedly, Matt, was hard, but you figured it out, to any picture. And so that's what machine learning is actually really good at. Instead of providing a series of steps to the computers, we instead give them examples of the right thing, and it figures the right steps out on its own. It sounds really mysterious. It really isn't, but that's the crux of it. Machine learning problems now are, instead of thinking of algorithms that you should be doing, instead you are thinking about the data that you have, the examples that you have, and hoping that certain machine learning algorithms can actually generalize that. But it always starts, and if you went to Tess's machine learning, perfect. All of that was perfect. I'm going to go over just a tiny bit to refresh, just a tiny bit to solidify this. But it always starts with a question, and it has to be a really sharp question, and there's only really 5 types of questions that machine learning can answer. Right, and she said, I think almost exactly the same thing, right? So she's making sure I'm saying the right thing. I'm excited that she's here. Now, if you think about it, all a machine learning problem, like think about a self-driving car, you can diminish that down to a series of yes/no questions, right? Like, should I turn left? Should I turn right? Should I hit this person? I feel like it's too soon for that joke, though, right? The answer is no every time, right? But if you look at machine learning, there's really only 5 types of questions that machine learning can answer, and they all have these really fancy names. I gave this talk, no joke. I taught kids like how deep learning works at a junior high, and I realized at that moment in time that us adults come up with really fancy names for things to feel important. And I told them this, and they were like, oh yeah, that makes sense. And I'm like, gosh, man. But if you think about it, these are what we call them: regression, classification, clustering, anomaly detection, recommendation, right? And they belong to certain classes of learning, one called supervised, where we give it the right answer, and another one called unsupervised, where we say, here, do something, right? And usually that has to do with clustering, anomaly detection, recommendation, that kind of thing, okay? So let's talk about this process. Now, Tess has much better pictures than I do, and she actually expanded it out a little bit more, so I encourage you to watch her talk. I put it into only 4 steps, but hers are much more explanatory. So you always, once you have the question, you have to identify if you even have any data. For example, Matt would never be able to make the cat picture thing work if he didn't have a picture of a cat. Same with any other picture, right, that you want to learn from. And we're going to be working specifically in vision, if that's okay. Once you do that, then you need to find a way to explore, analyze, and code, because these algorithms only work with numbers. And if you're working with text, it's still only going to work with numbers, so you got to find a way to convert it over. We're not going to spend too much time on that. Again, I encourage you to watch Tess's talk on that. Once you do that, then you build this thing. By the way, As you're doing this, you might only stop at step 1 and be like, we don't have the data, we can't do anything. That's okay. You might stop at step 2 because you've drawn a really cool scatter plot and you realized, oh, this is the feature or this is the thing that completely determines everything about my particular machine learning problem. And that's okay too. But then when you build a model, you use that model to predict. Okay, and we're going to be talking specifically about supervised learning and prediction with TensorFlow in this case. The way machine learning algorithms work is you pass in these things called features, and particularly with supervised learning, this thing called a label that has the right answer. So imagine like a huge square of data that has one column is the right answer, and then or maybe a couple columns are the right answer, and then a bunch of other columns are the things that we learn to predict from. Okay. So another question is, how do you know if it's doing well at all, right? Because you build this thing, by the way, called a model, and think of a model as just an asset in a program, and actually going to show you a real-life model and put it into a real program so you can see this is not mysterious at all. How do you know if it's doing well? Well, what you do is you kind of separate your data out, and you take 80% maybe. You can do 90 depending on how many records you have, but you use the bulk of it to train your algorithm, right answer, paired with the example features, and then you use the 20% to test it. In more modern applications, you actually separate it into 3 different sets because you have these other things that go into algorithms, and we'll talk about those. And so you train it with 80% with a certain hyperparameter for an algorithm, and then you test it with the dev set, and you do this loop forever and ever and ever until you think you have the right hyperparameters, and then you test it on the balance of the 10%. So that's the more modern approach. By the way, if you have any questions, just raise your hand, and I will make sure to repeat it so everyone can hear it, because I want you to really understand this, because I feel there's too much voodoo magic associated with AI that it kind of makes me sad, right? This stuff is not as hard as people make it out to be. Now, to make things even more interesting, there is a really specific notion of what right or good is for a particular machine learning algorithm. When you are thinking of accuracy, you're thinking of this bottom corner. How many did we get right? But sometimes we want to know, like, hey, if we guess true, how good are we at that? Right? You can see that that's this column over here, the one that says true, right? So I'm sorry, if we guess true, which is this one over here, how good are we at it? Or how good are we at guessing truth? Now, an example of thinking about this, that's the difference between precision and recall. When you're looking at a cancer detection algorithm, and we've built these things at Microsoft that look at an X-ray and say, oh, there's cancer there. If you're not sure, what do you want to tell the patient? Go see a doctor, right? We have a little app that will look at your skin and will say, hey, you should go see a doctor. Okay, does that mean we're optimizing for precision or recall? Well, it depends, right? If we guess true, how good are we at that? Or when we guess true or positive, how good are we at that? Now, I'll let you think about that because it really depends. Because also, if you're looking at Azure Machine Learning Studio, another thing we have, you can actually use a slider to optimize between precision and recall as well, which is super important. All the other things also have a name, which is really interesting. Okay, so now we're going to go back to Matt's problem of this boss that keeps coming down with some amazing problems. Now she wants Matt to actually, now that he's been able to figure out how to flip the checks properly, she's like, we want you, Matt, to actually read in the handwriting of the numbers inside of the check. Because you know there's a little box. Do you use checks in Norway anymore? No, of course not, because we're backwards in the United States. So there's back in the day when there was horses and stuff and buggies, they would like write numbers inside of this little box and these things called checks that work kind of like money. Just FYI for those of you that are here in Norway. So in the little box, we would write numbers and little dots, and that's what we would do. So now Matt, because they have to accept checks from the United States, has to be able to learn to detect those handwritten numbers. They look like this. Now, your programmer lizard brain right away is thinking, I could do this by just thinking about it. right? I could think of like, I'll just sample pixels in the middle, right? And if they're in the middle, mostly that's a 1, right? And you keep thinking, right? Your program, like we can't help ourselves as programmers. We'll keep, and then if it's a 1, right, we'll have an if-else statement inside, because if there's some more like dark things at the top, it's a 7, right? And now you've written this algorithm that has these weird if statements that you need to go home and take a shower afterwards because you wrote that. You wrote that. And a lot of us have written code like this where you have a lot of if statements and you go in there and you have to change it, and then you change a 0.5 to a 0.7 and you have to take a shower that night. We've all written code like that. That's machine learning where it works really well. So what we're going to do is we're going to talk about how we actually get this, because that's what you want, right? You want to pass in the picture and get a number out for each one of those numbers. That's what you want. So we're going to build that. Machine learning in particular is designed to build a very generic function that takes in something and responds out with the right thing. In this case, I want you to think specifically about numbers. We want to pass in a picture, and these pictures we all have are 28 pixels by 28 pixels. You pass it in, and then it spits out a number, the right one, as often as possible. That's what you want. So the question then becomes, well, what does X look like, and what does H look like? So in order to talk about the actual X, what I'm going to do is I'm going to simplify the problem just a little bit, okay? And it's going to be okay if we use our programmer lizard brains to start, but then we're going to have to simplify it a little bit more, is what we're going to do, okay? So this is the problem we're going to work on now. This is just a 9-pixel thing, right? And what we want to do is we want to guess if it's darker at the top or darker at the bottom. Yeah? Super easy. The computer gets this, right? The first one, the first line corresponds to the top left-hand picture. Top left-hand picture. And for those of you that know all about colors, yes, I know 255 usually means white, but I backwards it so that we could actually see it, okay? And I know also for those of you that are picture wonks that each pixel usually has 3 or 4 numbers, right, if it's RGB or RGBA. But what I've done is I've grayscaled it down to 1 pixel, okay? So for all you picture nerds, I got it. So as a programmer, you would look at this and how would you solve this problem? Darker at the top versus darker at the bottom. It's okay. I used to teach high school, so awkward silence is only awkward for you. Yes, sir.
Sum the first 3 values and set up some form of threshold. It's bigger than that, it's dark, it's smaller.
So the answer that he's giving me, John's giving me, is sum up the values at the top 3 and then set up some threshold, right? Great. You could also sum up the top 3 and sum up the bottom 3 and then look which one's greater, right? So what we're going to do is we're actually going to do something a little bit different than that feels kind of similar, okay? And so this is where I'm going to start to get a little crazy, but go with me, okay? We're going to make this, okay? At the bottom, we have all of the numbers for each value of those pixels, okay? So like 255, 104, right? And then we're going to try to come up with a very nice W for each one of these things, such that when we multiply each of these numbers and add them together, it's going to give us the right answer, okay? Now you're like, this doesn't make any sense. See, and this guy already knows. He's like, well, how about 111 for the first 3, right? Because if you multiply, that's literally like adding them together. And then he's saying -1 for the last 3, which makes them all negative. And when you add them up together, what happens? Well, it's either going to be negative or positive. If it's positive, we guess darker at the top. If it's negative, we guess darker at the bottom. If you didn't follow, that's okay, because I'm actually going to go through some examples. Now, this thing that we just did looks a little like this, okay? We're going to stack these numbers up, and we're going to call them like a special name. Does anyone want to call them something? How about we just call them vector, like vectors, because it feels vectory to me, okay? And this thing is actually called a dot product. Did you know that? That thing we just invented? We didn't invent it. It's been around forever. But here's a funny thing about the dot product. If we have a fixed W vector with all of the W's in there, let's just say it's 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. If we fix that, for every X that we give it, there are certain classes of X that always make the dot product 0. Did you know that? I'll give you an example. Let's just think in 2 space, or 3 space, because we're in 3 dimensions right now. Let's just say we have a W here and an X here, and the origin is right here. Vectors also represent lines, right, in space from the origin, right? And the angle between them tells us a lot about their dot product. It turns out that if the angle between them is 90 degrees, the dot product is always 0. It's true. They proved it. So if we hold a fixed W for every X that we give this thing that equals 0, it forms a line. In 3 space, it forms a plane. So that this W vector, right, everything that if we dot it with everything in the universe, all of the things that make it 0 forms a plane. And everything that's on one side of that is positive, and everything that's on the other side happens to be negative. And so we found a mathematical way to take this goofy little picture that I made and separate it into positive versus negative, right? Positive meaning top, negative meaning bottom. What if it's 0? Then they're equal. Think about it, right? If the top 3 pixels, we add them together, and we subtract the bottom 3 pixels, and they're 0, it means that they're equal. Right? And that's an interesting thing. So let's move on here, because I want to show you that it actually does separate the line. But you were probably wondering, well, there's this thing called a B, right? Did you see that originally? I'll tell you what that is in a second. So let's go through an example, right? We're going to come up with, we're just going to put the ones there for now, and notice that we get the positive 495. So that one, make sure that it's positive at the top. Here's the second example, right? We're going to stick the negative ones there, and you see we get minus 234, and that means that the bottom is darker. Do you see that? I want you to look at this, because I think it's important. Notice that the pixel values are at the bottom, the X's, and then when we multiply them together and add them up, we get that thing at the bottom right-hand corner, minus 234. Okay? So this is the ones and the zeros, like you said, and this is for the one that's darker at the top. This also works. Now, what does that little b do? Well, let's just say we want to guess. We just want it to be just a tinier bit darker at the top, and that still counts as a positive. Well, if we add a positive number, that will bias our guess towards darker at the top, right? Because, so let's just say we bias it by 100 positive. That means that the top cumulatively can be 100 less than the bottom, but we're still going to guess top. If we put a negative 100 as the bias, that's going to force us to guess bottom more often. Do you see that? It's kind of a bias. We'll call it like a bias for top or bottom. Now, as I go along, you're going to start to hear some terms that machine learning people use, but I am going to actually use it in the right context so you can see. This is a real thing called the bias, right, that you have in almost all machine learning algorithms. Now, the reason why you need that, and let me go back to this picture because I think this is what helps. If you just keep a W with no bias, that means that plane that we talked about is centered around 0. But if we add a bias, it moves it either positive or negative. You remember y equals mx plus b, right? If you just have the mx, it was centered around 0, the line. But the bias or the y-intercept moved things over. Think of it like that, yeah? Super easy, okay. So far, so good. So, any questions about this? We're good so far, right? Okay. So this is machine learning. Sorry. I mean, I don't know what else to say. This is it. This happens to be a linear discriminator, is what we call it in fancy grown-up terms, right? We take these 9 pixels, we do a W transpose times the pixels plus B, and if it's positive, we guess top. If it's negative, we guess bottom. That thing is called the model. That's it. I feel bad, right? Everyone's like, I feel like there should be more. Well, from the hype, yeah, it's not. This is it. You're like, but Seth, there's more stuff. Well, there is, right? But I mean, how much more can there be? Because you might be saying, well, Seth, I'm going to be even more cleverer. And what if, Seth, I wanted you to guess whether it's top, middle, or bottom? That's much harder. No, just make 3 of them. Right? And then we'll stack them up. And we'll call the stack of vectors after my favorite 90s movie, The Matrix. And then when we multiply this vector times the matrix, the one that has the highest output is the one we guess. Top, middle, or bottom. Right? This is dumb. I know, it's dumb. I don't know what else to say. But again, if you're having a hard time with this dot product between a matrix and a vector, just think of it as like the Cookie Monster. I'm dumb. I think of stupid things. So I take this X, like imagine I'm pulling it out, and I flip it over, and then I like go num, 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 and do a dot product with each one of those things. And then I get the 3 answers out. Remember, you take, flip, num, 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 and then you get the output. Okay? It's easy. Like, I'm not kidding. I taught this to like 6th graders, and they're like, oh, I get that. I'm like, crap, I'm going to be their janitor one day in their huge building because they're going to figure out machine learning and blockchain, and then there's no stopping them. Okay, so we figured this thing out. We know how this works. We've come up with an algorithm now that we feed in this 9-pixel thing. We do a W transpose X plus B. It gets top, middle, or bottom. In our case, the B is 0 because we came up with this fancy matrix, right? The B is 0, but that's okay. We'll still put it there. But in reality, we actually wanted to do this, right? That's what we wanted to make. That's okay. By the way, this is what this looks like. If you squint, you'll see the number. Do you see it? What number is that? 0, right? This is 28 pixels by 28 pixels. In this case, same like I did before, I reversed them. And so the intensity in the middle, right, indicates how much is in there. So that's what it sees. What we do, like in the other problem, like we just did, it just happened to be 9 pixels. What it is, we stack them together. And then we have an output. Notice that that one at the top is 0, 1, 2, 3, 4, 5, 6. That's 7. The second one, oh, I have the screen right here. This is helpful. The second one is 0, 1, 2. The third one is 0, 1. What's the fourth one? That's an example of a 0. The fifth one is 0, 1, 2, 3, 4. What's the sixth one? It's a 1. You see that? And so we're giving the computer, just like I said, examples of the right thing. Here are the number pictures in numbers, and here is the right answer. It's called a one-hot encoding. One-hot encoded, which means that from 0 to 9, right, we're putting a 1 in the vector wherever the right answer is. Okay? Because that's how we set it up. So my question for you is, what does, now that we did this thing, what does this one look like? Well, we want the answer to be 0 through 9. So what does that vector look like? Well, it looks like this. The answer, 1 through 9. Oh, it should be 0 through Yo, no, 0 through 9. Wait, no. Yeah, that's right. 0 through 9. So if there's a 1 at the top, we guess 0. You see that? Now, the vector that comes in is 28 by 28. How big is that? You are right, 784. Well done. So what does that make our W look like? Well, simple. 0 through 9. It's a big W, right? That's what that is. It's exactly the same thing that we just did. It's just that when we put it in linear algebra, it's still W transpose X plus B, because all math is for is to summarize several paragraphs into a small, compact notation. Math is all about being lazy, which is exactly what programmers are for. So it should be the same thing. Okay, so hopefully that one makes sense to you. But now the real question that you have is, it was easy to figure out the W and the B for that other problem. How do we get all of these huge W's and B's, right? Because we have a 9 by 784 matrix plus B, which is again going to be 9. How do we find all of those? Because, like, you can try to figure out those numbers on your own and go home and take a shower, or we can have the computer figure it out, okay? And to do that, we're going to use a little bit of magic. Not so much magic. You'll see exactly what it is in a second. The essence of what we want to do is we want to minimize the amount of mistakes we make with these W's and these B's, right? We want to minimize the mistakes. We want to make the mistakes as small as possible. How do we do that? Well, what we're going to do is we're going to come up with a function that describes how bad we are at it, and then we're going to try to make that function's value as small as possible, okay? So we're just going to make one. It's going to be a little mathy, but it's okay. It's okay. Remember, H is the model function that tells us the right answer. Y happens to be the right answer. So if we guess 0, and the right answer is 0, what does this equal? Well, 0 minus 0 is, if we guess 1 and the right answer is 1, 1 minus 1 is, so anytime we guess right, the answer is 0. Anytime we guess wrong, the answer is not 0. So we want to make this function as 0 as possible. Kind of like your loser cousin. I didn't want to bring up your loser cousin, sorry. You remember, though, that that's what our H function is, right? And so we want to minimize it with respect to all the W's and all the B's. How do we do that? Well, let's just come up with something. There's got to be a way that we can do this, okay? So pretend that the function looks like this. It doesn't. Well, it kind of does, right? There's a square in there. And that big sigma sum. By the way, this is the average error, or something called the mean squared error, for those that want the fancy term. So let's pretend it looks like this, okay? And you're living in this space. By the way, what's the lowest? This is x squared. What is the lowest value this function can be? 0. Okay. Okay. So pretend you're a blind 1D man that lives on this U. Let's call it a parabola. And I'm sitting on the number x equals 3. How high am I? Well, if I'm at 3, x squared, 3 squared is 9. So I'm standing at 9. Am I at the lowest point of this thing? No, but I'm blind. How do I know in which direction to go? Well, you sort of just feel around. So if I'm back here and I put my foot back, it's going up. That's a wrong direction, right? If I put my foot forward and it's going down, I should walk in that direction. So there's got to be a way for us to figure out like this slope, because this blind 1D man doesn't know anything about anything. All he knows is he's got to put his foot forward and got to put his foot back and got to measure the slope. So let's pretend that he can do that. So what we're going to do is we're going to take a little piece of y and a little piece of x, and we're going to divide it. We'll just call it dy by dx. Okay? And that will tell us the slope. And then Newton did something really funny a long time ago. He made those d's go to 0 and still measure like the slope. That thing is called a derivative, and what you just learned is calculus.
Thank you.
Yeah, I know. I didn't come up with this stuff. It was invented, I think, in England, which is why they probably have maths and we only have one everywhere else. So this thing is called a derivative, right? It tells us the slope at a single infinitesimal small point. So the blind man can ask the derivative, what is the slope? And then he can make a decision about where to walk. So let's see what that looks like, okay? Oh, too much, too many. Oh, that one was scary. I will just tell you that the function, the derivative of x squared is 2x. I'll just tell you that. Like, the thing about math is once you put it in a formula, you can literally stop thinking completely. You just, and then everything happens. Like, for those that remember calculus, x squared, you just take the exponent, you move it to the front and subtract 1. So the derivative of x cubed is 3x squared, right? You don't even have to think about it. It's really dumb. So again, remember, we're the blind 1D man standing at x equals 3, right? So we know that at x equals 3, x squared is 9. What's the derivative at x equals 3? Well, 2 times 3 is 6. Which way do we want to walk, negative or positive? Well, if we're at 3 and we want to go to the 0, we need to walk in the negative direction. So what we'll do is we'll subtract the derivative value from where we are, okay? That's what we're going to do. So I'm at 3. I'm going to subtract the derivative, which is 6. So I'm going to walk 6 the other way, okay? So I'm at 3, 2, 1, 0, minus 1, minus 2, minus 3. Okay, blind 1D man, you kind of went in the right direction, but we have a little bit of a problem. So what he's going to do is he's at minus 3. Minus 3 squared is also 9. The derivative of being at minus 3 is minus 6. So we're at minus 3, and we're going to subtract a negative 6. And there's no such thing as subtraction, only addition of negative numbers. That's another trick that's super helpful. So what we're doing is we're minus 3 plus 6. So we walk, and now, again, minus 3 plus 6, or 6 minus 3, puts us back at 3. So we have a little bit of a problem. So the derivative is not enough. We actually have to scale the derivative by a fraction so that we don't walk all over the place like an idiot. And that thing is called the learning rate. And what you've learned is something called gradient descent. I know. I keep like unmasking things. I was like, oh, the emperor has no clothes. We do. It's just math. And for those of you that want to be pedantic, it's actually the gradient of the cost function, which is an upside-down triangle, right? Because the derivative is only in one dimension. The gradient is with vectors. But it's just like each one has its own derivative. Okay? So what we do is we take a current W or a current B that we have. We can just guess the first one. Just guess it. It can be all 0. Don't start with zeros. That's bad. Start with like something uniformly at random. Right? And then what we do is once we start, we say, okay, we look at this W, and we're going to subtract off alpha times the gradient. And then we get a new W. And we do this forever until the cost function is as 0 as possible. Make sense? Okay, so I've showed you a lot of stuff that you're like, well, you promised us TensorFlow. I did. But I wanted to show you that when it comes down to it, you are effectively modeling this stuff that I just showed you, okay? So we talked about all this stuff. We have x, the incoming image. We have y, the right answers. We have the model function, which is h of x, w transpose x plus b. We have the loss or the cost function, which is called the squared error or mean squared error. And then we have the optimization method, which is gradient descent. You have all the tools to implement something in TensorFlow now. Okay? They're all there. So with TensorFlow, the cool thing about it is that we have to do two things. Now, for those of you that know about the newer stuff of TensorFlow, there's something also called eager execution. I'm not going to talk about that. But in TensorFlow, what you do is you define a graph of computation, and then you run a training session. Guess what you're defining in the graph? Something like this. What does that look like in TensorFlow? Well, it looks like that. By the way, you're like, well, this model is kind of weird, but look at it. Like it literally looks exactly like we just described. Do you see that? Like it's exactly what we talked about. It's W transpose X plus B. In TensorFlow, we have things called variables and placeholders. Variables are the things that TensorFlow can optimize, right? Because we want to optimize the W's and B's. The placeholders are promises to put values in for it to use. That's it. So that's part of the graph, but we also need to describe the error function too, right? Or the cost function. That's what this thing looks like. Now I just drew the graph, but if you're a programmer, you know that when you're defining operations, it's actually creating an abstract syntax tree that then gets converted into something. If you're C#, it's IL, right? Otherwise, it's machine code if it's C or C++. But that's what, if you look at TensorFlow, it's literally just defining here, we're reducing by the mean hx minus y quantity squared. Do you see that? I mean, it's not super hard at all. And then finally, by the way, there's other stuff in the graph that we're going to build. I'll just show you that in code just so you get a sense. But we also need to know how accurate it is, because notice that the cost function doesn't talk about accuracy at all. We have something called how do we optimize it, and then how do we debug and get some summary of this stuff. All right, so let's take a look at this goodness. I am here in let me start this up here. I am here in Visual Studio. You can run this all in Visual Studio. I'll show you some of the cool things that you can do in Visual Studio with this stuff, but I'm just going to run it straight Python so you can see what's going on, okay? So, right here, we have everything that I talked about. There's the X, there's the Y, there's the linear model, and the linear model is all the way up here. All right, W transpose X plus B. And then we're just going to name that, that's our prediction. These scopes allow me to actually get those nodes of the graph. Because when I produce it, you'll all of a sudden see, oh, I see what this is making. Okay, so I'm going to scroll down. And then what I'm going to do is I'm going to talk about the accuracy. So the accuracy is a little different, right? Because remember how when we had that top, middle, bottom, it just returned big numbers? And we just had to do like the argmax of that thing? Like the index that was the largest, that's the one that we guess. You can see that that's what we're doing with the accuracy, right? We're just measuring, like of our h of x function, let's just measure the index of the biggest one, and then just return the biggest one. And we're going to do that with y, and then we're going to see if they're equal, and then we're going to do an average over them. So notice that the cost function is different than the accuracy function. Accuracy is just saying, did we guess the right thing? The cost function is trying to find the best W's and B's. The model function returns a vector with numbers, and you pick the one that's the highest, return the index, okay? Now let's talk about how to do gradient descent. And as you probably suspected, it's super hard. I'm just kidding, it's not hard at all. And by the way, there's the cost function that I was telling you about. So that's it. Now what we do is we just train the model. So what I'm going to do is I'm going to go over here and show you what that actually looks like. Now you're probably thinking this is a lot of code. It's not. It's a lot of code for me to see what's happening. But in reality, what I'm doing is I'm taking the digit values. There's 60,000 of them. And if you give it all 60,000, you can make the right matrix, but it doesn't learn that well. So what you do is you take the 60,000 and you chunk it up into things called batches, and you run through it. And so let's just say our batch size is 1,000, right? And we're working with 50,000. Then that means that there's a batch of 1,000, and there's 50 of those batches, and that constitutes an epoch of training, okay? And you can see the loops right here. This range is going for each of the epochs, and that epoch is something I pass in. How many do I want to run them? And then what I do is I enumerate through the training X and the training Y for the size of batches. Now, I wanted to abstract that away, so I built my own digits class in Python that initializes it, and so I literally just have to do a for each, and it returns the right batch size, and it stops when it's done. You can look at it. By the way, this code is all available. I'll give you the link at the end. So I just want you to understand what's happening, okay? All right, so yeah, we loop over it. And then the last thing that I want to say is the cool thing is you can also do these things called summary scalars, so that as you're running, you can just like see how your accuracy is doing, how your cost is doing. By the way, we want the cost to be 0, and want the accuracy to be 100%. So as this thing runs, if the accuracy isn't going up or the cost isn't going down, stop. Something is wrong, okay? All right, so once we go in there, you'll notice that for each of these batches that we're doing, we are creating a session in TensorFlow, and then we are executing these things with, remember we promised it an X and a Y? With the values that we promised before. And then what we do is we write out like our summary values, which is what epoch we're on, and along with what cost is. And by the way, in the summary thing that we actually defined is this merge summary operation that keeps track of the cost and the accuracy. That's it. And so we run the summary op, we run the cost op, and we run the optimizer. And then we store those and run it. Let me show you what it looks like when we run it. Okay, so I'm just going to say python train.py. And I already have some default values that do the right thing. Now, it's going to think for a second because that's what Python does. The other thing that's interesting as it's running is that, like, I want you to think of a device that's really good about multiplying matrices. The GPU, right? That's why GPUs are so powerful when it comes to actual machine learning, right? You can see that it's actually using my GPU right now. This will take about 60 seconds to train and get the appropriate W's and B's. You'll also see that the accuracy per epoch should be going up, and it maxes out at about 82%. There you go, 22 seconds, and I saved the model out. That's it. Now you're probably wondering, well, what do those things actually look like? So let me go to Explorer dot here, and let me go to the output over here. And notice that I have these things called logs, which are super handy. I'll show you what that does in a second. And then we have these things called models, which is the output, and you're like, oh man, that's a lot of file vomit. There's two different models that it's actually working with, two graphs. One is the graph that has the optimization, and then there's another graph that I exported that only has predictions. So for the optimization graph, hold on to your hats. It looks like this. I don't know what this means, if I'm being honest. But what's happening here is this graph represents the actual optimization of the W's and B's. But then when we actually want to do like prediction, we don't need all the optimization stuff. So there's a step called freezing a model, which swaps out all the variables for constants. And what you do is you say, this is the output node, and then it creates sort of the linear tree of what it wants. And then it freezes those variables and makes them into constants. And so the output that we actually get that we're going to use for inference is this one. Guess what it looks like? Multiply the A and B, add Y, which is W transpose X plus B. Here is the thing that we learned. There's the W's. There's the B. That's it. Remember I told you this, what was the size of the W going to be? You see that? 784 by 10. That's it. And now what do I do to make this work? Well, I'm going to take this little digits file, this digits.pb. I'm going to go over here to this thing called digits, and I'm going to just replace it. And now I'm going to go to my WPF app and start this guy up. And in theory, what I should be able to do is I should be able to actually write a digit and have it be recognized. So let's do one that it will guess right. Oh, that's not good. So 9. By the way, this is not the smartest model, and we have, oh, jeez. You're so dumb. Okay. You're probably, oh, thank you, yeah, thank you. By the way, it's supposed to not work because I just did the dumbest thing you would ever do. I made a linear model when I could do a deep learning model, which I have not done yet. But let me show you what that code looks like so you can see that I'm actually bringing it in, right? What I'm doing is I'm loading up the actual bitmap of the thing, and I'm resizing it to 28 by 28, and I'm grayscaling it and flattening it out, and then I load up the graph. I fetch the actual node that I wanted. Remember how I said I named it like prediction with model? That's how I pull it up. And then I just return the right value. So if I were to do this again and do a recognize, you'll see out here the P value, and we pick the one that's the highest. Do you see that? So I'm running out of time. So I want to show you something even smarter. By the way, there's the output. And I didn't show you this other thing. I got to show you. Oh, I hit the wrong button. This other thing, which is really cool, let me hit stop here, is I can actually run this thing called TensorBoard direct from Visual Studio. I am going to go to my output and my logs and hit OK. And what it's going to do is those summary values that you saw, it actually graphs them out for me to show you what it looks like when it's running it. Okay, here we go. Give it a second. There you go. There's the accuracy going up. There's the cost function going down. Okay? All right. So another way of looking at this model is like this, right? We have all the x's going in, we multiply it times the w, and then you have a thing coming out, right? So is this deep learning? No, it is not. It's just a linear model. It separates things that are linear, but what if your stuff looks like this? Then it won't separate it. So why don't we be super clever and we'll stack them, right? We'll have an output X, go to a new output, and then we'll just do a ton of things. Is this thing deep learning? No, because a linear combination of a linear combination is still a linear combination, and you can prove that using something called mathematical induction. It's super easy, right? So what you do is you have to add a nonlinear function inside each of those little circles that does some kind of weird curviness. We'll call that function the activation function. Okay? Now it's going to start going like really fast, okay? So hold on. So the question is, once we have an activation function, how do you find the derivative of this function so that we can optimize it? Well, it turns out that derivatives are funny in that the derivative of a function that contains another function is a derivative of the outer function times the derivative of the inner function. So if you want to find the derivative of the out, you have to find the derivative of that function and multiply it times the derivative of h3. And then to find that derivative for h3, you have to find that one times the derivative of the other one, and it backpropagates all the way. So the clever people that made this up called this algorithm backpropagation. So you move forward to inference, move back to actually find the derivatives, to find the right W's and B's for every one of those layers. And you're probably wondering, what does that look like in code? Well, I'm glad you asked. I'm going to go over here and change this to something called MLP better. This is called a multi-layer perceptron. And one of the things that I did not show you is that because W's and B's happen so often, and they're part of layers inside of TensorFlow, then you can see actually that you can actually set, you could have originally just said, use a dense layer that has inputs X and unit outputs 10. Now, what I want to do is I'm going to make a multi-layer perceptron with 2 hidden units, 512 by 512. And notice that all I'm doing is I'm doing last output is the X one. So last output equals a dense layer, pass in this thing. The units or the size is going to be 512, and there will be 2 of them. We're going to stack them together, and then we're going to have an output. So let's run that one and see if it does any better. But what I'm going to do is I'm going to be a little bit more clever, and what I'm going to do is I'm going to change this optimization function to something that's a little bit better. Like how I typed without typing? This is called the atom optimizer, because remember how the gradient descent 1D guy just went around all over the place like a crazy man? Atom optimizer is very succinct about not shifting too far as it goes down, and it takes a more direct path to the output. All right, so let's run this one and see what it looks like. Just going to run it again. Exactly the same way. Did I hit save? No, I did not. Ah! I keyboard interrupted it. Okay. Now, we can load it up. By the way, was it running the right thing? No, it wasn't. Good. So now I fixed it. Okay, so now it's running again. Whoa! Did you see that? What are the accuracy? By the way, what was the best accuracy we got before? It was 82. What is it at now in the middle of training? Wow, that really helped. 29 seconds, we finished with an accuracy of 97%, just by stacking it. But it's even smarter than that. By the way, that's what the graph looks like. I did the example. You can actually be even smarter than that, because when we're looking at these pixels, remember how we just lined them up? How does like if you're looking at the 2, notice that this pixel and this pixel are very important to each other in proximity, but when we stack them, it doesn't really do a good job. Well, why don't we just make this little thing? We'll look at pixels around them. We'll call them convolutions, and then we'll stack them on top of each other again. So this is called a convolutional neural network, and this is what this looks like. What we do is we're looking at pixel squares now, and then passing those forwards in the network, and then pooling them together, and then doing another convolution, and then doing that together. So let's run that one and see how well that one does. So I'm going to change this cost function to something else, because there's other cost functions. I'm just going to change it to that one. And I'm going to do this one to convolutional neural network better. I'm going to save it, and I'm going to run it. And how could you get better than 97? Was it 98%? Can you get better than that? Well, I hope so, because otherwise this talk would suck. And as it's going by, because I'll let it train. But remember how this thing was in here? I'm just going to do a little bit of a refresh here, because it's still looking at that whole folder that we just saw. Take a look at this goodness. That was the second one we ran. Do you see how it's a little bit smarter than the first linear one? Here's the one we're running now. By the way, can you see what percentage it's at already? All right, so as it's running and as I'm finishing up, hopefully you've seen like how TensorFlow is actually taking the math that's important and it's actually generalizing it into a way that you can train these particular things. By the way, did you see that thing load up in the back as it was going? Hopefully you've seen that it's not something that's so mysterious that you cannot do. Hopefully you've also seen that like this magic that happens works really well with a ton of different kinds of pictures. And here's another thing. You can actually take someone else's W's and B's that you learned, and you can put them into your algorithm. That thing is called transfer learning that you might have heard about. And now this is done. You can see that it is should be all refreshed. And you can see that if you look at the accuracy, if I were to hide this one, because that one's kind of polluting everything, you can see that it actually is getting smarter than the one before. And again, just like I did before, remember how I had the actual learned digits here? In the output, I have a third model. I just take that one, Control C, move it over to this one, Control V, replace. And now, when I run this program, it won't make as many mistakes. So I'm going to right-click, debug, start new instance. And if I did everything right, that model should just be able to be replaced, and it should be able to recognize the 3. So you'll see over here, the output's a little bit different, but notice how good it is at knowing that that is indeed a 3. Like, it's really confident. So I'm going to hit F5. There's a 3. I'm going to take this off and then do like a 4, 8, 4. He wants me to do this 4. You see what I'm saying? And so, like, that first demo was bad on purpose, and now what you're seeing is that with a model that's trained and a little bit smarter, then it's a lot better. And the reason why it's called deep learning is because that model that I built at the end was actually had a lot of layers stacked on it. But again, it's just W's and B's that we've optimized using calculus. So we did that. All right, so just a little bit of a summary. Machine learning is all about finding the h of x, giving the examples instead of steps. Deep learning is one way to do it. Now, there is some ambiguity as to what constitutes how many layers you need to do deep learning. I don't know how many it is, but it's more than 5, I guess. Some of the models that they're building now are like 50 to 100 layers. It's pretty amazing. We need an x and a y. We learned about the model function. We did a linear model function. We did multilayer perceptron, and then we did a convolutional neural network. We talked about the cost function. We used mean squared error. I also kind of snuck in cross entropy loss because I knew that would work really well with the multilayer perceptron. It doesn't work really well with mean squared error. Finally, we learned gradient descent and atom optimizers, which are really good about optimizing the stuff. Now, here's the Azure bit. It was nice that I could run it on 30 seconds on my machine, but we actually have these machines called deep learning VMs where you can run up tons of these jobs all at once. The more information you give it, the better. We also have something called Azure ML, which keeps track of your parameters and keeps track of like how well your models are doing. We also have something called Batch AI that lets you project and push all these things out to tons of GPUs that you can run them all over the place. By the way, there's the code. If you want to get a hold of me, there's my email address or tweet at me. Thank you so very much for your time. Any questions? Yes. I mentioned transfer learning, yes. Yeah, so remember how, so here's an example. Let's just say you wanted to detect the difference between a dog and a cat. You can actually take something called there's a model that's been trained on ImageNet that you can pull their W's and B's over and then just put a layer on top of it. And so you take their W's and B's, their neural network that they trained, and you can freeze those layers. And then as the picture goes up, it has some weird intermediate representation that then you can take into your own dense layer and do a prediction. That's called transfer learning, where you're actually borrowing someone else's W's and B's to do training. That's right. So he said, so you can use some extra training on top of their model to train your specific thing. The answer is absolutely right. Yes, sir. Oh, yes, absolutely. Any other questions? Yes, sir. So do you change the approach that much if what? Oh, okay. So the question is, do you change the approach if it's an audio versus an image? Absolutely. The thing about science that most people don't realize is that science is glorified guess and check. That's all it is. So when someone asks me, like, how do you know how big the network should be? How do you know what learning rate to use? How do you know? My answer is always going to be, just use science. It turns out that for those kinds of models, recurrent neural networks are better because they deal better with sequences. Same with text. Any other questions? Okay, hopefully that was helpful. I'll be available all over the place. Oh, sorry, one more.
I just want you to do this one more thing.
Yes.
Can you draw a 9 upside down?
Can I draw a 9 upside down? Sure. I don't know if I have the skill to do it, but I will try. You're saying like 9, so a 6.
No, 9 upside down.
That's a 6. Oh, okay, so how about that? Whoa, crap, that's actually pretty good. I'm afraid of it now. But you shouldn't, right? I hope you realize that now you actually seen me make this from scratch, and it took like, what, was it 80 seconds? So I just want you to know that this is not magic, it's all engineering, and now you should have a ton of questions regarding what data do I have, how do I put it into a space that machine learning can understand, how do I run these models, how do I do experiments? Those are the right questions, not is general AI going to kill me? That's a stupid question, and that's one that marketing has generated for us. Thank you so much for your time. Have a good rest of your conference.